Welcome back. We're still in section 1.4. We're going to be talking about domain of a function. Now keep in mind, domain is a set of all of the inputs. So it's all of the real number inputs for which the expression is defined. Now there are some exclusions to domain, and there's two main things we need to look for. We need to avoid dividing by zero, because division by zero, you get undefined. You're not going to get a nice real number. And you want to make sure you don't take an even root of a negative number. Because once again, with the even root of a negative number, you're going to get an imaginary number, not a nice whole real number. Not a nice real number, I should say. So now, for number 1, for example, if we're looking at the domain, what we're going to do is we're going to set x squared minus 4 equals 0. So you add 4 to both sides, you get x squared equals 4. Take the square to both sides, x equals plus or minus 2. Now, think about the number line here. We got our negative 2 and our positive 2. These are the only numbers we cannot use. It's all real numbers. X does not equal negative 2 or positive 2. So we want to write this in interval notation. Put open dots. We're going to put shading in between, shading to the left, shading to the right. So we have 3 shaded portions. We have 3 intervals. We have negative infinity to negative 2, parentheses at both, the union of negative 2 to 2, that middle interval, and the union of 2 to infinity with parentheses around all of them. That's our domain in interval notation. Like I said, I think about the interval notation like the number line and how it's graphed. It's just putting each shaded region, whether using a parentheses or a bracket for that region. Now for number 2, because it's the square root, we want to make sure that x is greater than or equal to 0, because we can take the square to 0. So if you're going to write that in interval notation, think about the number line. Here's our 0, solid dot. So our interval would be from 0 to infinity. That would be the domain for that example. For number 8, it's a weird problem because it's just a set of ordered pairs. It's not like all the other continuous functions. So our domain is just our input values, our x values, in numerical order, no repeats. So negative 3, negative 1, 0, 2, and 4. That's our domain. For the other ones, their domain is going to be intervals or continuous. For number 19, 1 over x plus 5. Set that denominator x plus 5 equal to 0. X equals negative 5. So if you're thinking that number line, here's our negative 5. That's the only number we can have. We can have everything else but that. So our intervals, negative infinity to negative 5, parentheses around both. And for our other interval, it goes from negative 5 to infinity. And once again, we put parentheses around both. That's another way to write all real numbers, x not equal to negative 5. So we have it 2 ways, in interval notation and our more traditional way. Number 20. Now in number 20, we're going to set our denominator equal to 0. X times x squared minus 9 equals 0. So we can factor this, or we could set each factor equal to 0. I'm going to do that. X equals 0, that's taken care of. And then x squared minus 9 equals 0. So we add 9, we get x squared equals 9. Take the square to both sides, x equals plus or minus 3. So if we were to think about this on the number line, we have a negative 3, we have our 0, and we have our positive 3. We're going to have open dots at all 3, because those are the 3 numbers we can't use. So we're going to be shading all the way to the left here, in between, and to the right. So we have 4 intervals we need to write down. So what we could do is our intervals we're going from negative infinity to negative 3, parentheses at both, the union of, now the interval from negative 3 to 0, so parentheses, negative 3, 0, parentheses again, the union of 0 to 3, in parentheses, and then for the final one, going from 3 to infinity. Notice all of these are parentheses. That's the same as writing all real numbers, x does not equal 0 plus or minus 3. So here's interval notation in a more traditional notation. Number 21. We have a square root, an even root. So 2x minus 6, the number underneath the radical, has to be greater than or equal to 0. So we're not taking the square root of a negative. So we're going to solve this inequality. We're going to be adding 6 to both sides. So 2x is greater than or equal to 6. Divide both sides by 2. X is greater than or equal to 3. So if we think about the graph for this, here's our 3. We're going to use a solid dot, and we're greater than or equal to, so we're going to go to the right. So interval notation, we're going from 3 with a bracket, because of the solid dot, to infinity. Or traditionally, x is greater than or equal to 3. So there's our two ways to write it. The more traditional way at the bottom and interval notation up top. Number 22 is a more complicated problem. Now, it's a square root, so the number under the radical, 4 minus x squared, greater than or equal to 0. What makes this more complicated is it is a quadratic inequality. So to solve this, the first thing we're going to do is we're going to treat it as an equation. I'm going to change it to 4 minus x squared equals 0. We'll worry about the inequality later on. So I'm going to add x squared to both sides, so I get 4 equals x squared. Take the square root of both sides, so I get x equals plus or minus 2. Now I'm going to graph this on my number line. I'm going to have my negative 2 here and my positive 2 here. Now, because of the or equal to for the inequality, and this is something that happens with a quadratic inequality, I'm going to put my solid dots on my number line this time. Now, I want to pick a point on the number line. I'm going to pick a point in between. I'm going to test x equals 0. I want to see where my shading belongs. So I get 4 minus, now x is 0, so 0 squared greater than or equal to 0. Here's where inequality comes back into place. We get 4 is greater than or equal to 0. That's a true statement, which means that that 0 is a solution. So our solutions are going to lie between those 2 points. So I would write this, my domain, I would write it as, with brackets because of the solid dots, negative 2 comma 2, and that's my domain. In a more traditional way, not in interval notation, negative 2 less than or equal to x is less than or equal to 2. The only values we can use as inputs are the values between negative 2 and positive 2, including those numbers. And now for problem number 23. A little bit different again. Volume equals 4/3 pi r cubed. It's the volume of a sphere formula. Now we know that for us to have a volume, the volume must be greater than 0. So in order for us to have that, the radius must be greater than 0. Because if we don't have our radius greater than 0, if it's 0, then our volume would be 0, which doesn't exist. There's no volume there. If we had a negative, our volume would be negative, and we can't have a negative volume. So r is greater than or equal to 0. Think that number line again. Open dot at 0. Shading to the right. So our interval notation for that would be a bracket, parentheses, 0 to infinity. So there's our interval notation and our more traditional for r. In problems numbers 24 and 25. Now it says use your calculator to graph. So take out your calculator and graph these. And you'll see for problem number 24, here's -2, here's +2. So it reaches that point and that point, and our graph just goes like that. That's what the graph looks like. So really what's happening here is we're shading in between. So our inputs are going to be between -2 and +2. So the domain in interval notation, -2 and 2 with a bracket at both because of those solid dots. Or more traditionally, -2 less than or equal to x, less than or equal to 2. And that's why problem number 22 is in between, because that's what the graph looks like. Now, number 25 is similar, but we switched around where the x squared and the 4 are. So if you were to graph this on your calculator, you'll see here at 2 a dot and at -2 a dot, and it goes like this. Which means we're not going in between, we're going in opposite directions. It's an OR inequality. So our domain would have two intervals, from -infinity to -2, parentheses, and a bracket at -2 because we reach it, and the union of, at +2 we put a bracket, to infinity. That's our domain in interval notation. Or, in more traditional notation, x is less than or equal to -2, or x is greater than or equal to +2. We'll finish up with a few word problems. Number 26, the fireworks. So they owned a bookstore called the Book Nook. So the number of books, B, in thousands at the Book Nook is sold, modeled by that function. And we just want to use that function to estimate the number of books sold since 1994. Now, T is the number of years after 1993. So to find out what T is, it's going to be the year we're looking at, 1997 minus 1993. So our value for T is going to be 4. So we're just substituting our values. So for B of 4, it's going to be 4 squared plus 26 times 4 plus 400. So B to the 4th is 520. So the number of books is 520. Since B is in thousands, 520,000 books. Not just 520, but 520,000 books. For 27, once again, we're evaluating this function. So we want to find out, will it clear a 10-foot fence 300 feet from home plate? Now we're given the equation, and f of x is going to be telling us what the height of the ball is at any point. So if we're looking at 300 feet from home plate, we're looking at f of 300, negative 0.0032, times 300 squared, plus 300, plus 3. So when you use your calculator to type this in, you get 15. So at 300 feet, the ball is 15 feet above the ground. So yeah, if here's our 10-foot fence and the ball is up here, it cleared the fence. It cleared the fence by 5 feet. Because this function is giving us the height of the ball. Number 28, the zucchini plant was 8 centimeters tall when it was planted, and it grows about 1.5 centimeters per day. We're going to write a function expressing the height, h, in terms of the number of days, d. So now it started at 8 centimeters. So that is our y-intercept. Our starting point is at 0, 8. And that 1.5 centimeters per day is our slope. So we can say that the height h is 1.5 d plus 8. And finally, problem number 29. So, soft drink company with a new can, narrower than the old can. So for our experimental can, the ratio of the height to the radius is 4. So what they're telling us is that the height to the radius is 4 to 1. That's our ratio. That's actually a proportion. So we're going to write the volume of the can as a function of the radius. It's a cylinder. Volume equals, so volume in terms of R is going to be pi R squared times H. Now we want to have the height written in terms of the radius. So what we could do is we can take this proportion and cross multiply. H equals 4R. So instead of putting H, we can put 4R in its place. So the volume in terms of the radius, R, is pi times radius squared. So instead of the height, we can put 4R in its place. We can substitute. So volume in terms of R is going to be 4 times pi, radius squared times R is radius cubed. That's a function for the volume in terms of the radius, R. Now we're going to write the volume as a function of the height. Once again, we're going to put volume in terms of height, pi R squared times the height. Now, we know that the height is 4 times the radius. If we want to get the radius by itself, we can divide both sides by 4. So the radius is the same as H divided by 4. So it's going to be pi. Now instead of writing the radius, it's H over 4, and we're squaring that, times the height. So volume in terms of H is going to be pi. I'm going to put that over 1 as a placeholder. And now it's H over 4 squared. So we square the numerator, we square the H, we get H squared. We square the denominator, 4 squared is 16, times H over 1. I'm just putting that as a placeholder, because now we multiply the numerators. Volume in terms of height, pi. H squared times H is H cubed over 1 times 16 times 1, which is 16. And that's a function for the volume in terms of the height. And that is the end of section 1.4. Thank you.